In the previous video, we have learned about program blocks and how it is being used in the program using the assembler directive use. So in this video, we will be learning about program blocks and the control sections. And in program blocks, how we are arranging the codes in the memory. So as we all know, assembler during the two passes, it performs different operations. And if it encounters with the program blocks, what the assembler does, that we are going to see. So a separate location counter will be managed for each block. It saves and restores LOC CTR when it switches between the blocks, and at the beginning of the block, the LOC CTR value will be set to 0. Assigns each label and address relative to the start of the block. So each when it encounters with a new block, LOC CTR value will be set to 0, and when it encounters any label, then it will be assigning address relative to the start of the block. So it stores the block name or the number into the SIM tab along with the relative address of the label. Then it indicates the block length as the latest value of LOC CTR for each block at the end of pass 1. Assign to each block a starting address in the object program by concatenating the program blocks in a particular order. So this is the format in which the data will be stored in the SIM tab. So it will be having either the block name or the block number will be there. Then it address based on the starting address, you will be storing it in the SIM tab. Also the length of the code also will be there. So a default block, once it encounters with the CData block, it will find its length, and that length will be stored in the length of the default block. Then the next address will be 0066 for the CData block, and its length will be 000B when it encounters with the next block, that is C blocks. So in order to find the starting address of C block, what it does, it adds the address 0066 plus 000B to get this address 0071, and it will be having some size which will be treated as the length of the block. In pass 2, it calculates the address of each symbol relative to the start of the object program by adding the location of the symbol relative to the start of its block and the starting address of this block. Okay, so in pass 1, relative to the start of the block, it will be finding the address, and it will be stored in the SIM tab. And in pass 2, based on the start of the object program, it will be calculating the address for each symbol, and that will be based on the location of the symbol within the block, that is the starting address of the block. And how the address is being calculated, some examples we can see, like for example LDA length. It is stored in some memory location 006 inside the default block is 0. So the address of the value of the operand length, this length will be defined elsewhere, and that length address 003 relative to block 1. So length variable will be defined in block 1, that is the CData block. The relative address will be 0003 inside that block 1. So address can be found out like 0003 plus 0066. Why the 66? It is the starting address of the CData block, is equal to 0069. Relative to the program, that is starting address of the program. So when this instruction is being executed, program counter value will be equal to 009. That is current when the program is fetched, the PC value will be 0006. When the instruction is being executed, PC will be incremented by 1. LOC CTR will be incremented by 3, which becomes 0009. So the displacement can be calculated like, now the target address is 0069 and the LPC or the LOCCTR value is 0009. So the difference can be taken and the resulting addresses obtained will be, that is the displacement field will be 0060. So hence in this displacement field you will be getting 060. So the for the format 3 instruction, opcode will be taking first 6 bits, and NIX BPE, N and I will be set to 1, indicating the symbol addressing mode. Program counter relative, hence it is P will be equal to 1, and the displacement what you have obtained from the calculation 060. Hence you will be getting the result as 032060. Similarly, we will be able to generate the object program for each program blocks. So it is not necessary to physically rearrange the object generated code in the object program. The assembler just insert the proper load address in each text record. The loader will load these codes into the correct place. So instead of treating the whole program as a single block, since here separate blocks are there, so separately the information will be stored. So here also you will be having header record, text record and end record. Header record is of this header record will be having a program name, starting address, length of the program, and text record it will be having the starting address of the text record, its text record length, the maximum length is 1 which means 10 records you will be inserting in that particular text record. When if it requires more beyond that limit, then a new text record will be created with its starting address and length. Similarly, it will be done for the rest of the codes also. So here it will be arranged as in program that will be loaded in source program will be like default 1 C data 1 C blocks, then default 2 C data 2 default C data 2, which means the read recorder function, and then comes the write record subroutine default 3 and C data 3. So object program will be created as like this. Then program loaded in memory will be like default 1 2 3. The default blocks will be grouped together, and then C data blocks will be grouped together, and C blocks will be at the end of the it will be towards the end. C blocks. That is how it is loaded in the memory. Okay, so based on this address, based on the address here, you will be storing the value inside the text record. Then the next is the control sections and program linking. Control sections can be loaded and relocated independently of the other control sections. Most often used for the subroutines or the logical subdivisions of the program. The programmer can assemble, load and manipulate each of these control sections separately. Because of this, there should be some means of linking control sections. So in control sections, mostly it will be used for the subroutines. So this can be implemented using the assembler directive csect. And how it will be used, section name will be given followed with the assembler directive. So in this case also, separate location counter will be managed for each control section. It will be used for subroutines, and we will be using assembler directive csect, and it will be managing separate location counter for each control section. Then here it makes use of some symbols like external definition symbols and external reference symbols. So what does that mean? Means external definition in which the names or the symbols will be defined inside the control section and may be used in some other control sections, some other sections. So such symbols or names will be defined using the directive extdef. Okay, so external definition and external reference, it will be indicating some labels or instructions, the labels that is defined in one control section, but they have to be referred in some other instructions or data which is located in another section. So in order to identify between the two, we make use of this extdef and extref. For external definition, if labels are given, means those labels or the symbols will be defined in the same control section. If external reference, some labels are given, means those symbols, they are used inside the control section, but it is defined somewhere else in the control section. For example, if external reference RD, REC and WREC is used inside the control section, means it means that RD, REC and WREC is used inside the section, but it is defined elsewhere in the memory or in the program. So this is how it is used in the program that we have learned earlier. So we are having RD, REC and WREC. So these are defined elsewhere in the control section. So our first control section is this one, that is copy. The program copy is the first control section. So in that case, RD, REC and WREC is treated as the external reference symbol because it is defined elsewhere in the program. Here see external definition, buffer, buffend and length is treated as external definition symbols because buffer, buffend and length is defined in the same control section. So it is mentioned with the directive extdef. In case of second control section, that is RD, REC, CSEC, section name followed with the directive CSEC, it makes use of the reference symbol buffer, length and buffend, which means that buffer, length and buffend is used within the control section, but it is defined elsewhere in the control section. Buffer, length and buffend, it is defined in the copy program, that is the default section. Here also the same. Write record, it is a third control section in which the external reference symbols length and buffer is used. So how the assembler it handles the reference. So in this case, RD, REC is the external reference symbol. So assembler doesn't know where the RD, REC is being stored. So for that case, it inserts an address of 0 and it only uses the extended instruction format. In this case, it uses the extended format because it doesn't know where the RD, REC is stored, and sometimes it may be away from the instruction that is being used. So it uses extended format. This information will be passed to the loader. And in other case like max len, buffend minus buffer. So here two external references are used, that is buffend and buffer. In this case also the assembler inserts a value 0 and passes the information to the loader. So what you have to see is buffend and buffer, if this expression is used in the same control section. That is buffend and buffer, if it is defined in the same control section where the expression is used, then in such case the address will not be generated. It will be evaluating or calculating the result simultaneously. That is a case 3. Okay, and if buffend and buffer is not defined in the control section, in such case it will be generating the address value as 0. So that is case 2 and case 3. Buffer and buffer if it is defined in the same control section and different.